This is question number 45 from electric current in conductor from HC Verma. We need to find out the equivalent resistance between given point between A across A and B here, across A here and B here, one point on the one of the circumference here, between A and B here, between A and B here, and between A and B here. So the first is should be easy. The second, third, and fourth has a slight trick where you need to move those external, let's say this is, assume it's to be a copper wire. I need to move it around so that the resistors start looking like either a series resistor or a parallel resistor. The fifth problem has another trick where you need to apply the principle similar to use in kind of Wheatstone bridge and solve it. So let's go start with the simpler one, the first one, where we need to find the equivalent resistance between A and point B. So we see that these two resistors are in series, so this R plus R becomes 2R. Now this 2R and this resistor R here, they are in parallel. So the equivalent resistance will be 2R plus R, 2R into R divided by 2R plus R, 3R. This will be 2 by 3R. Now 2 by 3R is like this. We need to find the equivalent resistance between point A and B. 2 by 3R plus R is added, that becomes 5 by 3R. Now 5 by 3R and R are in parallel. So 5 by 3R into R divided by 5 by 3R plus R. This 5 by 3R divided by 5 plus 3 divided by 3, 8 by 3R. So this becomes 5 by 8R. 3 gets cancelled. So the next one, let's move on to the next one. And this is a little slight trick in it. The trick is how we can see it as a series set of series and parallel resistance. What we need to do is we need to converge everything on this circumference at one particular point. This resistance is touching here, this resistance is touching here, and this resistance is touching here on this part of the circumference, while essentially this is a copper wire and all these points are a single point. So we need to find that one point where we want this to converge everywhere. So let's say we want to converge everything on this point. So what we do? We take this resistor here and try to rotate it like this, in this fashion, till this end touches this one. So that's what I'm showing here. This I'm rotating it here. So this start moving around this and then finally touches this point. In the same way, this resistor here, I'm going to rotate it around like this till this one starts, this end of this resistor start touching this point. And finally we can move around this point B anywhere on the circumference of the circle, which is wire, to assume that this is actually the point here. If we do this exercise, we get this resistor R here, and the resistor that was here is now lying like this, and the resistor that was lying here is now looking like this, and the point B that was here, that can be here. And the wires of this resistor can still lie like this. They don't reduce or add or reduce anything from the circuit, but they are kind of redundant. Doesn't affect our calculation. So these three resistors are in parallel. Their equivalent resistance is R by 3. And then we have this R by 3 resistor and R in series. So the total resistance will be R plus R by 3. So now there's something wrong here. This calculation is a mistake. These two resistors are in series, so it's R by 3 plus R, and that will be 4R by 3. Now the next problem, it's a similar problem. Point A is here, point B is here, and we need to find the equivalent resistance between this. So this problem is same as the Wheatstone thing we learned earlier in one of my YouTube lectures. You can search for this on this channel. Let's assume that we have a voltmeter connected on this point. What happens is that the current flows from here, goes through this branch and returns through this branch like this. And the current can also flow from here to here, the lower branch, and can return through this. Assume that for the moment these two resistors are not there. So what happens is that the voltage divider created by A, X and B, let's assume this point is X, and that voltage will be exactly half to the voltage difference between A point, B point, because these two resistors are equal. In the same way, if there's a current, because of this current flowing here, there's a voltage divider, and voltage at point Y will depend upon the voltage dividers R, this small r and small r. Because of the symmetry of this whole thing, the voltage at point X and voltage at point Y are exactly same. It means we do not see any flow of the current through this resistor. Which means if we connect a voltmeter, if we connect a voltage source, then we see that it sees a circuit that comprises of these two resistors here and these two resistors here, and we can eliminate these two resistors for our calculation of the equivalent resistance between A and B. Anytime you see a symmetrical resistor and you think that by connecting a voltage source between these 2 points, there will be no flow of current in any of the circuits, then you can just eliminate these resistors from your calculation. So by eliminating these two resistors, R and R, we get a circuit simplified to this. R plus R, 2R, 2R, 2R and 2R in parallel. Equivalent resistance will be 2R divided by 2 or R. Let's move on to this problem number D. We have a point here A and B on the circumference. This also is the same problem. We need to collect all the end points which are lying on this long copper wire at one particular point. So what we do here is we keep A here, and then we move this point, this resistor, like start moving this resistor like this. And the same way we start moving this resistor, this end of this resistor, toward this direction. So it will move something like this. And when we do that, and the same way this resistor, this end of this resistor, we start moving like this, that's so that it will also converge to the same point. And when we do this exercise, this is the resistor right here, this one, and when we move this resistor to the like this point comes here, so this becomes like this resistor. For this resistor, when it moves all the way to here, this end, it looks like this. And finally, the resistance here, we hold this edge of this resistor and move it like this, then the end of this, it connects to point B. So all we are seeing is 4 resistors in parallel, and the equivalent resistance will be R by 4. And finally, we have the last structure where we have these 5 resistors. This is also a symmetrical problem, and the thing that we need to look at is that again we connect a voltage source between point A and B and exploit the symmetry. We see and focus on the resistance, on the voltage on the two ends of these resistors. Because of the symmetry, the voltage at this point is going to be the voltage at this point. To further clearly understand it, assume that this resistor from here is mentally removed. We have a current flowing from here, goes into this resistor and returns to this point B to the circuit. Another path is the current flows like this, this, and this. Now when the current flows like this R, resistors R and R makes a voltage divider, and we have some voltage at Y. In the same way, we have a current flowing in this branch, and because of that there is a voltage drop, some voltage at point X. because the ratio of these two resistors R and R is same as the ratio of this resistor R and R, or 1:1, we know that the voltage at X and voltage at Y is same. That means there is no current flowing in the resistor that is here. And that's the reason we can eliminate this resistor from our calculation. And given that, the circuit simplifies to a circuit like this. There are two resistors, the two top resistors are here, R and R in series, and then these two resistors are also in series. And finally we get RR to 2R, and this RR 2R. 2R and 2R are in parallel, so equivalent resistance is 2R divided by 2 is equal to R.